Let's talk about just a capacitor connected to an alternating source. I've pulled the equations from our current test notes so that they're here already. We're going to walk through these equations. So, alternating source, oscillating with time. We're still assuming this cosine function for the source. For the capacitor, because of Kirchhoff's loop rule, as we go around the loop, we find that the source voltage at any given moment in time must equal the voltage or potential difference across the capacitor at that same moment in time. Since we're writing our source voltage as a cosine function, and Kirchhoff's loop rule tells me that both the source and the capacitor have to have the same potential difference at the same moment in time, because there's no other elements, that means we can write the potential difference across the capacitor as a maximum voltage across the capacitor times cosine omega t. Okay, that's what this first equation is representing. So similar to the resistors, this lowercase v represents the instantaneous value, meaning the value of the voltage at whatever time we're talking about. And this is specifically the capacitor. That's why we have the subscript of C. Capital V sub C represents the maximum potential difference across the capacitor. So if we were graphing the capacitor's voltage as a function of time, this would be the maximum value of that potential. The rate at which this omega, this oscillation rate in radians per second for the capacitor, is the same as for the source. Now, if you recall, capacitors, just when we talked about them originally, we said that the potential difference across a capacitor was equal to the amount of charge on the plates of the capacitor divided by capacitance. That's still totally true. The amount of charge on the plates of the capacitor is equal to the capacitance times delta V. But delta V is changing with time. That means Q is going to change as well. So we can say the charge on the plates of the capacitor as a function of time is equal to C times our equation above. That represents the voltage drop across the capacitor. Now, to go along with this theme of lowercase letters representing the instantaneous value, that's where this second equation comes into play. Lowercase q means the charge on the capacitor as a function of time. How much charge has accumulated on the plates is going to alternate with time because of this alternating source. So that's what the lowercase q represents. Now the amplitude here, C times this capital V, we could write that like I did over here as a capital Q. This would represent the maximum charge on the capacitor. The amplitude, the maximum value the capacitor ever sees. And I guess I need to actually write this consistently. This will now just be the capital V sub C, because that's what we're using to represent the maximum potential difference. Now current is going to flow. Current will flow clockwise, sometimes it will flow the opposite direction, counterclockwise, sometimes. The amount of current that is flowing in this circuit with just the capacitor, so that sub C, is equal to the rate at which the capacitor is charging and discharging. So taking the derivative of this function, derivative of cosine is negative sine. We're still going to have that amplitude there. And then we have to take the derivative of the omega t, which is omega. And so we find the current in this circuit as a function of time is negative omega c, capital VC, sine omega t. Okay, two things here. This is a negative sine function. That means if I come back up to my graph and I want to graph current as well, at time equals 0, the current is going to be 0. A negative sign means it oscillates downwards first. It turns out we're just shifted from the voltage. So when the voltage is maximum up here, the current is 0. When the voltage is 0 right here, the current is a maximum, just the negative is a specific direction. When we get back to a maximum voltage, the current's back to 0. So it'll reach a maximum here, go to 0 here. So the current in the capacitor as a function of time, we'll use a capital I sub c to represent the maximum value, and then the lowercase I sub c to represent the current function. So the current in this circuit is totally alternating with time. The voltage drop across the capacitor is also alternating with time, but they are not in phase with each other. These two are out of phase. So the current is 90 degrees or pi halves ahead of the voltage for the capacitor. Ahead meaning if I was to trace back my graph representing my current, the current would have had its peak before that voltage. So this is just describing the phase shift. Now, this is also stated here, the peak current leads the peak voltage. Peak meaning maximum. So the highest value. It leads the peak voltage by 90 degrees. Okay? That's going to be important when we draw our phasor diagram. So phasor diagram, if I were to draw a phasor representing the peak value of the capacitor's voltage, the phasor that I draw representing the current needs to be ahead of that by 90 degrees. Since these phasors rotate counterclockwise, I need to come ahead by 90 degrees and draw this current phasor that represents the current that would be flowing in this circuit that has a capacitor. This piece here is going to be important especially when we pull in and attach a resistor and capacitor together. So let's keep that in mind. But let's come back to our equation down here for current, which, by the way, we have that up here from the test notes. But I want to talk about this amplitude for a minute. Any number or numbers we have in front of the sine function represents the amplitude, or the maximum, or the peak value of whatever this function is describing. Since this function is describing the current at any moment in time, so the instantaneous current, we can say that the maximum or peak value of the current in a circuit that has just a capacitor is going to equal omega C VC. Omega, this omega is the rate at which this system is oscillating. If we come back over to the source voltage, it's this source, I kind of scribbled out omega there, sorry. The source is alternating with time. That omega right there is the angular frequency of that source voltage. C is the capacitance. Capital V sub C is the maximum potential difference the capacitor will potentially see. I want to write this a little bit differently. V equals I times this omega C. Well, I had to divide it to the other side to get it with the current. Now, the reason I want to write it this way is because we know a volt is equal to an amp times an ohm, right? V equals IR. But we can't say this is R. It's not a resistor. But this term right here has to have units of ohms. We call this a capacitive reactance. Sorry, I was totally pronouncing it so that I could spell it right. So capacitive reactance, we use an X and a subscript of C, 1 over omega C. This has units of ohms. This is kind of a resistance to the flow of current. How much current can flow in our circuit depends entirely on this reactance. So we can write this equation this way. And similar to resistors, if we had a bigger resistance, that made less current flow. And that's ultimately what this shows us. That X sub C, this capacitive reactance, is not in and of itself a resistor, but it is measuring kind of the resistance to the flow of current. Meaning, the bigger XC is, the less current, the smaller the maximum current will be, and vice versa. That XC depends both on the frequency at which the source is oscillating, omega, the angular frequency specifically, and then the value of the capacitor. So omega is still 2 pi f, but this tells us that how the capacitor affects the flow of current in the circuit not only depends upon the capacitance itself, but it depends also on the rate at which that source voltage is oscillating. These equations, I've kind of moved off the screen a little bit at the top, but these two that we've just talked about are right here. So the capacitive reactance, X sub C, is defined as, that's those 3 lines. The definition is 1 over omega C. And then this peak current value that flows in the circuit, because of only a capacitor, is going to equal the voltage maximum value of the capacitor divided by this capacitive reactance. If X sub C is big, then I sub C is smaller. So the capacitor will help control how much current will flow. Or maybe not control, it affects how much current will flow. That might be the better way to put it. If we think in terms of a capacitor charging and discharging, omega, if it's really big omega, meaning a really fast oscillation, means a small X sub C. Ultimately, if we think about the capacitor needing time to collect charge and let charge accumulate on its plates, and then discharge, and charge, and discharge, and charge, and discharge, this small X sub C leads to a large I, assuming the same voltage. So in the same circuit, this one capacitor connected to the same source, if all we do is adjust the frequency, and thus the angular frequency, that will cause X sub C to change, which in turn will affect the maximum amount of current, that peak value. Small X sub C, we can think of that as the capacitor doesn't have time to charge and discharge as much as it possibly can. It potentially could charge more if the frequency didn't alternate so much. And vice versa is true. A small omega, a very slow oscillation rate, would lead to a large X sub C, which would mean a small I. The capacitor would have plenty of time to charge. If you remember capacitors, if they reach a full charge, they stop the current from flowing. Now, it's not going to stop it completely, but it's going to mean the peak value of current is just not as big, because the capacitor has plenty of time to charge and discharge. So we're going to put together our resistors and capacitors and look at an RC circuit next.